So it's just 3, 5/3, you're done. This was the one on the test where people were like, well, I know the answer is 5/3. They already knew that when they started the problem. They're like, I know it's 5/3, but I still required that you like rip it all apart and do it. Now we've got this, right? Pretty good, yeah? How about this one? Limit x goes to infinity of x squared over e to the x. Where's the numerator headed? Infinity, right? That's going to infinity. Where's the denominator headed? Infinity. How do you know that's going to infinity? Is E, okay, so this goes back to last class as well, right? Remember when we did the graph of E and we said e to the x looks like this? And I asked you what happens as you go to infinity? We said it goes to infinity. So as you go to infinity, this right here goes to infinity. So you have infinity over infinity, right? So can I use L'Hopital? Yes. So according to L'Hopital, the rule, derivative of that is 2x, and derivative of the bottom, thank goodness, is just e to the x again, right? Did that help or no? We still have infinity over infinity, don't we? We can do it again, right? Because if we're here, right? If we're here, we have infinity over infinity again. It's almost as if, forget that this ever happened. Let's say that was the problem I gave you, right? Then you would say use L'Hopital. So I'm going to use L'Hopital again. So you can use L'Hopital more than once, as long as you're getting 0 over 0 or infinity over infinity. So a second application of L'Hopital's rule is derivative of the top here is 2, right? Derivative of the bottom is itself. Now what's happening? You have a constant on top, fixed number on top, right? I said fixed. I didn't mean to put 0. Okay, that is a fixed number, right? And then the bottom is headed to infinity. That is not infinity over infinity. That is not 0 over infinity, right? But that is something we know what happens, right? Number on top is fixed. Bottom gets huge. Ratio gets small. This goes to 0, right? So this limit is 0. Yes?
This still works when the numerator and the denominator, even though they both go towards infinity. Like, let's say they're opposite signs.
Even if like one of them is positive and the other one is negative, it still works. How about this one? X, let's go 4x squared plus x minus 1 over, I don't know, x squared minus 3x. Yeah, that's it. Oh, I forgot to tell you where x is going. Sorry. X is going to infinity. L'Hopital. L'Hopital. It's an awesome rule. As far as I remember, L'Hopital didn't have a ton of contributions to math, but this was a big one. When you compare it to like Newton, right? Like Isaac Newton, like just a ton of stuff. There's a lot of mathematicians that did a lot. This is, I believe, he only did a few things. So, what?
Was the rule?
What's that?
When did he create it?
I don't remember. I'll have to go back and look.
Did he contribute any other fields or just math?
I'd have to look it up. I'm going off of, I know I've researched him a little bit, but I don't recall that he did a lot more than this, but I could be wrong, but I don't know. I have to go back and look. I never took like a math history class. Some people take like the history of math. Everything I did was just pure math stuff. So there are classes where you can go learn about the famous mathematicians, and everything is, I know, is just stuff I've read myself. All right. Do we have a form that L'Hopital's rule is valid for? Where's the numerator headed? Infinities, it's infinity, right? Because all this up here is just getting bigger. Here, these are subtracted, right? So I have infinity minus infinity. But do you remember when we did this, I told you that whichever one has the highest power is the one that dominates, right? So this is going to be infinity on the bottom, right? Okay, so we have infinity over infinity. So I apply L'Hopital. Here we go. L'Hopital. L'Hopital is great. Derivative top and bottom. Right? What do we have there? Infinity over infinity. Do it again. L'Hopital. 8 over 2? And that's, there's no x's anymore, right? So it's just 4. That's your answer. So students will always, when I give them L'Hopital's rule, they always sit there and they get frustrated. And they say, why didn't you just show us this to begin with, right? Like, why did we not just do this in the beginning? Why torture us? Well, why didn't I do it?
You like turning the screws.
No, no. I do, but no. There's a reason.
So we know exactly how to do it.
Mm-mm.
Because it doesn't always apply.
So what if I would have walked in here and say, hey, we're trying to do these limits, right? And if you ever get it 0 over 0 or infinity over infinity, you just do, do what? The derivative. What the hell is a derivative? You don't know what a derivative is.
So we should just skip limits altogether.
Right? You didn't know what a derivative was. So how are you supposed to take a derivative? Right? So this is actually one of these times in math where what happened was we start with the limit, which I told you in the very beginning. Actually, I'm going to show it a little more respect. I told you in the beginning of this class that the limit was the heart of calculus, right? That's cute. Right? The limit is the heart of calculus. And then from that, all these different branches come off of this, right? And one of them is this idea of the derivative. It's good, isn't it? It's good. So we come up with this idea of the derivative, right? And then from the derivative, we go different places, right? Related rates, you know, sphere is growing, blah, blah, blah. We do all this, but we wind up saying, you know what? We can actually use this derivative to come back and actually do limits again. Like we can use this as a tool to help us here. This happens a lot in math. What'll happen is you'll have, and if you look at math like a tree, right? There's all these little branches, big branches, smaller little branches, and then eventually you have a little leaf. So you've got like a person studying this very specialized area of mathematics. And they'll come up with some theorem, they'll come up with some statement, it'll be true and it'll be proven. And it's like, okay, great, you have this theorem, big frickin' deal, who cares, right? Every once in a while, there will be a theorem here that solves an open question over here. Like this person's like, man, if I just knew that this was true, then I could continue with my question and I could answer it. And then they go, oh crap, well you know what, this guy over here showed already that that's true. So I'm going to use that theorem over here. So it happens a lot of times in math where people are studying one area of math, like here derivatives, right? And they could keep going this way, but someone said, you know what, is there a way I can go back and use that here? And they found this connection. That's L'Hopital, right? Okay, I'm going off. Drawing hearts and trees. We need to get back to the math. Yeah, that's a cool one. How about limit x goes to 0 of e to the x minus 1 over e to the 2x minus 1. I don't know if I've ever done this limit before. I just made it up, so. What do we get? If we plug in 0 for x, what do we get? E to the 0 is what? 1. E to the 2 times 0 is still 0, right? E to the 0 is 1. 1 minus 1. We get 0 over 0, right? So this is 0 over 0. We can use L'Hopital. So by L'Hopital, take the limit. X goes to 0. All right, derivative of the top. E to the x over derivative of the bottom. E to the 2x times 2. That's going to work out pretty nice. What is that? You get e to the 0, which is 1, over e to the 0, which is 1 times 2, a half. That's the limit. Okay. How are we doing on time? We're doing great. Doing great. How about this problem? How about x plus 1? Let's go to infinity. X plus 1 over the square root of x squared plus x plus 1. Okay. So before you go and yes.
Now that we're learning L'Hopital's rules, are we still going to need to know how to do limits with the algebra trick? For the final?
From here on out, if I ask you for a limit, you do it however you can.
Okay.
So if you can use L'Hopital, use L'Hopital. Yeah, it's a tool. I'm not going to restrict you from it now. The only time I ever really was restrictive is when we were learning the definition of the derivative with the limit. And I did want you to be able to find the derivative with the limit definition a few times for me. Since then, we put it away. Now that you have L'Hopital, that's your tool. Use it. All right, but what about this one? What do we have first to start? What form do we have? What form do we have when we... No, what's happening when we take the limit here? Infinity over infinity. So can we use L'Hopital? Yes. Okay, so we can use L'Hopital. We do have infinity over infinity. Okay, L'Hopital. Shit, right? Do you see why this is not so nice? What's derivative of the top? 1. Okay, but what about the bottom? That's a chain rule, right? You're not going to get around that. That's a chain rule. So you have to take derivative of the square root of something, which is 1 over 2 square roots of that something, right? Am I done down here? Now times what? 2x plus 1. Yeah, that's the derivative on the bottom? Yeah? Let me clean that up a little bit so you don't go too far ahead of yourself here. I have 1 on top, right? And on the bottom, I'm going to slide this 2x plus 1 on top of the 2 square root of x squared plus x plus 1. Y'all okay with that? Just moving that thing over? I have 1 divided by a fraction, don't I? I have 1 over a fraction. So can't I just flip this over? So this is limit x goes to infinity. The 2 square root of x squared plus x plus 1 goes on top. And the bottom, it's 2x plus 1. And now I take the limit again. What's your question?
I'm lost again.
Yeah.
How do you know the 2x plus 1 doesn't go on the bottom when you do the chain rule?
Because you're multiplying, right? The derivative of the square root of something is 1 over 2 times the square root of what's here, right? So that's this. And then you're multiplying by the derivative of what's in there, right? Which I'm saying is 2x plus 1. You're going to do 2x plus 1. You look at it, if you're going to put it next to a fraction, you have to look at it as being over 1. So that's why I guarantee it has to be on the top. Does that make sense to you? Okay. Any other questions? Yes.
So I guess I kind of do for the derivative of the denominator, the chain rule for square root. I do mine a little bit different, but I've forgotten. Like mine is pretty much the same as yours, but yours is a little bit different.
Mine's better, right? No, I'm sorry, no. Are you doing the 1/2, all that's a
Yeah.
negative 1/2?
Yeah, so what are you doing?
I'm doing the same thing.
It's like but it looks a little different. So
Mine looks better. No. Okay, so remember when we were talking about the derivative of the square root of x, right? We said there's two ways to look, well, when we first learned it, I said this is x to the 1/2, right? And we're taking the derivative. And so we use power rule. The 1/2 comes out, then it'll be x to the negative 1/2. That's what you're using, yes? What I said is this is going to happen every time, right? Every time we take derivative square root of something, this is going to happen. And I decided I'm going to rewrite this. I'm going to clean it up. I'm going to make it look different. I'm just going to write 1/2 times this. I'm going to drop it to the bottom. 1/x to the positive 1/2, right? Just properties of exponents. And then I'm put those two together and make that 1 times 1, and then 2 times that is 2 root x. And this is what I recommended, right, to the class, that when you take the derivative of the square root of x, just remember it as being 1/2 root x. And that's what I'm doing here. I'm taking the derivative of the square root of something, so I'm saying that's 1/2 roots of the x. And then I continue with the chain rule, right?
yeah, it's just that I guess it's just preference because I kind of avoid complex fractions like the plague. So I just try to keep everything either on the numerator side or the denominator side.
I hear you, and that's fine, except that when we're trying to do limits and use L'Hopital's rule, we need a ratio, right? Because we need it to be infinity over infinity or 0 over 0. So you're going to need to make it look like a ratio to be able to do.
Yeah, just complex fractions always. I guess just the way that I write, I don't know.
Yeah.
I just always try to avoid that.
I would say try and get yourself more comfortable with going back and forth between the notations, because the notation you're talking about, I would want everyone here to be just as comfortable with that notation as well. But realistically, most students in here are not going to need to be able to go back and forth between those notations comfortably unless you're doing a lot more math. We okay? All right. What now? We have infinity over infinity again, don't we? Do it again. Do you really want to do it again, though? What's going to happen? Same thing. See, the derivative of the bottom is going to be 2, right? But on the top, aren't we going to do the same, like 1/2 root? I mean, we're going to have the same thing, and it's going to create another fraction again? And it's going to do that every single time. And I'm never going to get anywhere. I'm just going to keep going, going, going. Which means that as mighty and powerful as the L'Hopital's rule is, it's not the magic pill, all right? It helps us in most cases, but it has limitations. There are certain limits that we still can't get even with L'Hopital's rule. So we would have to go back and do this the good old-fashioned way, which would be to try and kill off the highest power of x, which means you'd have to put a 1/x on the outside of the root. That way when you forced it in, it would get squared and it would kill off the x squared. That's the clean way through this limit. You try L'Hopital, you're going to start getting yourself stuck into this massive mess. All right? So sorry, it's not the answer, the ultimate answer. Yes?
So would you usually tend to avoid using L'Hopital's when there is roots?
Like a root, I tell you, if I see a root, I'm like nervous. I'm like, shit. I would try the L'Hopital first, and I would just hope for the best. But the reason I'm stopping right here is because this actually looks almost exactly like what I started with. Because on this one, I had a linear expression on top, and I had the square root of a quadratic here. And now I have the same thing, except they're flipped over. And so I know that when I take this derivative, I'm going to get, this is going to go to a constant, and that's going to give me the same sort of fraction that I got a second ago. And it'll be a square root of a quadratic over a linear again, and then I'll be just going nowhere. But I wouldn't say that as soon as I see a square root, I'm giving up. I'm going to try L'Hopital. Like I really want L'Hopital to help me. Okay. We doing all right? There's some fun ones here. All right. So I'm going to just tell you, we still have 10 minutes, 12 minutes. I'm going to tell you right now, out of 3.7, what exercises I think you should look at. You already have a lot to do this weekend already, right? So let's just say for 3.7 for now, I would look at like 1 through 15, maybe just do the odds to start. We're going to spend another half class, at least half class on L'Hopital. All right, we're going to spend at least half of next class. So you'll have time to go back and finish or go and do more of these. I want to show you a new limit to end class with here. Limit you've never done. Limit. Trying to think of which one I want to do. Hold on. Do I want to go to infinity? Yeah, I like that one a lot. Okay, we'll do that one. Limit. X approaches 0 from the right of sine of x times the natural log of x. This is a good limit because it ties in some stuff we did last class. So I want to know what happens if you try and let x approach 0 from the right-hand side of this expression. So let's talk first about sine. What's sine of 0? 0. Okay, so this is headed to 0, right? No problems there. But this natural log of x is headed to where when you approach 0 from the right-hand side? Think of the picture of natural log from last class. Where is it going as you approach 0 from the right? Do I need to draw it? Negative infinity. Very good. This is what the natural log of x looks like from last class. And I said, we need to know in this class what happens when you go to infinity, and then also what happens when you go to, and I said we can't go to negative infinity, but we can go to 0. We go to 0, it dives down to where? Negative infinity. So this is headed to negative infinity. And they're being multiplied, right? We have never seen this before. In this class, we've never seen this. We've seen 0 over 0, right? We've seen infinity over infinity. We've seen infinity minus infinity. But I have carefully avoided this ever happening, where you have something that's trying to get really, really small, right? This sine function is trying to get really small. At the same time, this natural log function is trying to get really big but negative. And so you have to remember, I'm not saying that this is 0, am I? I'm saying it's approaching 0. And this is getting bigger and negative. So it's like, what happens when you get a really small number times a really big negative number? Who wins? You don't know, right? You actually have to know how small is that and how big negative is that. This is a toss-up. This is kind of like 0 over 0, infinity over infinity. We don't know who wins. This is a new type of form that we can get with limits that's like this, an indeterminate form. That's what we call it, indeterminate. We don't know what this becomes. We don't know what that becomes. So we're kind of like stuck, all right? Can we use L'Hopital? Well, L'Hopital says we have to have what? 0 over 0 or infinity over infinity. Is this 0 over 0? No. Is this infinity over infinity? No. Right? So we can't even use L'Hopital. You with me? So how do we deal with this? All right? How do we deal with this? All right? And I really want you to be paying attention to the fact that we have this, right? That there's on your formula sheets, do you remember that limit summary thing? Oh, wait, do I not have it here? I think I have it in my Cal 2 one. Yeah, I have it here. Remember this page right here, this with the boxes on it that shows the different types of limits and what to do? Right? Remember that? Look in the top left of this box. We have covered in here, we have talked about what to do with infinity over infinity. Now we even have L'Hopital, right? So we've got more tools for that. We know how to deal with that, and we know how to deal with that. We have not done that, or that. We haven't looked at any of those. And so what I'm doing is I'm introducing you now to this new idea of something getting really small times something getting really big. What happens? So there's a standard procedure for this. You ready for the procedure? It's going to look weird. What I'm going to do is this. Whenever I see that, I'm going to look at my two pieces, and I'm going to make a choice. And for this first example, I'm just going to make a random choice. I'm just going to pick one of them, and I'm going to drop it to the bottom. Now, watch what I mean. When I do that, when I say that, look at what I mean. I'm going to leave the natural log on top, and then I'm going to take the sine x, and I'm going to drop it to the bottom, which means I'm going to rewrite it as 1 over sine x. Do you all agree that I have not changed the problem? Right? 1 over sine x really is just a sine up there, isn't it? Now you might be sitting there going, what the hell are you doing, man? That looks like a stupid move. But now look what happens. As x goes to 0, we already know that that goes to negative infinity, right? But on the bottom, I have 1 over sine now, right? 1 over sine, 1 over, if x goes to 0, sine goes to 0, right? So you get 1 over 0, and fixed over 0 is going to become infinitely big, right? So this right here, the whole thing becomes infinitely big. And now what do I have? Infinity over infinity. And so now I can use L'Hopital's rule. Now you have to pay attention because the bottom it's sine x, right? 1 over sine x, right? So I really should rewrite the bottom as cosecant x before I take a derivative. Right, that's what 1 over sine is? I only did that because I need to take the derivative. If I ask you for the derivative of the top, could you give me derivative of the top? What is it? 1 over x? So we're good on this derivative, right? My concern for you is this. If I ask you for the derivative of this, how many of you are going to tell me 1 over cosine x? That's wrong, right? Because you would have to use a quotient rule on that. Or you'd rewrite it like cosecant x and go to your formula sheets and get the answer. But the derivative of 1 over sine x is not 1 over cosine x. You have a quotient, right? So you'd have to do derivative of top times the bottom minus derivative of bottom times the top. So I think it's better to just do this. L'Hopital. Here it comes. Okay, derivative of the top is 1 over x. Everyone said that, yeah? On the bottom, what's derivative of cosecant x? Formula sheets. Negative cosecant x times cotangent x. Wow, this looks like it's getting worse, doesn't it? Does this not look worse to you? It looks worse to me. How are we doing on time? Let's just try right now to let x go to 0. Let's just try and see what happens. If I let x go to 0, 1 over 0, that's become infinite, right? Can you plug 0 into cosecant? Well, that's cosecant, right? Can you plug 0 in here? Well, it becomes infinite, right? So we got infinity here, and then cotangent of 0. I don't know, this is a freaking disaster, isn't it? Looks bad? Looks bad? Okay, well, I'm not going to give up, all right? I'm going to keep going. I have 4 minutes. So here's what I'm going to do. None of your homework problems are going to be of this form, okay? All your homework problems are going to be of the form 0 over 0, infinity over infinity. Your next homework assignment will have these, all right? Want to add the rest of them? So how about I do some algebra here? Limit x go to 0 from the right. 1 over x on top. On the bottom, I'm going to rewrite this as negative 1 over sine x times cotangent is a reciprocal of tangent. Tangent, sine over cosine. So this is cosine of x over sine x. That's the same thing, isn't it? Now what I'm going to do is start maybe flipping some stuff around. This is a fraction. I can bring it up flipped over, can't I? And then this right here, I can bring it up and flip it over. So could I not write this as limit x goes to 0 from the right? I have the 1 over x that's there. I bring this and flip it, so it's going to be sine x over negative 1. And then the other one, I bring it up and flip it, sine x over cosine x. That's the same problem, isn't it? All right, let me see. Where do I have an issue? If I let x go to 0 right now, that's a problem, right? 1 over 0, that's a problem. This is not a problem, is it? 0 over negative 1 is not a problem. 0 over 1 is not a problem, right? So the issue really that I have right here is this x is giving me like a division by 0, right? And then I have a 0 on top from both of these signs. So this is the first problem you're seeing like this. So let me just continue. I'll show you what I'm doing next. You can tell me whether or not you agree or not. Limit x goes to 0 from the right. I'm going to rewrite this as sine x over x times negative 1 times sine x. I'll just do sine x over cosine x. That's just me moving things around, shuffling some things, right? Now the reason I shuffled it like that is because I recognize this. This is going to be 1. I either remember that from the formula we memorized, or I can do a L'Hopital on that, couldn't I? Like that's 0 over 0. I could do a L'Hopital on this, and that would become a 1. This is negative 1. Is this a problem? What do you get on top? What do you get on bottom? You get 0 over 1. 0 divided by 1 is not a problem. So that means this goes to 1, this one goes to negative 1, and that one goes to 0. And I no longer have 0 over 0 or division by 0, right? I just have 0. So the answer is 0. That's a tricky problem to start with. Should have maybe given you all an easier one. Okay, so you know what you need to do for homework, right? Don't worry about this problem. If you didn't understand it, we're going to do more of these, all right? What do you have? You have, what do you have? Oh, you've got the logarithmic differentiation problems from 3.3. You've got the inverse trig derivatives from 3.5. And then you now have some problems from 3.7, L'Hopital's rule. So have a good weekend. Yeah.
You too.
Yeah, have a good one. I'm sorry, my video from last class recorded, but the audio did not. It's like just pure static.